My name is Florian. I am similar to Davide, come from the pulp team at ETH Zurich. So we quite have some overlap. But in my past research, I've been mostly been focusing on the APU-based platform, on the Ariane, now CVA6-based platforms. But I have been employed and as the hardware and software director of task groups. So in that effort, I'm both managing the microcontroller-based platform and the application-based platform, and in particular, as a first shot target, the FPGA, which I'm giving you an overview today. You can reach me on Twitter or by email. So if there is any questions you, for some reason, don't want to ask now, just go ahead and you can contact me privately as well. So with that said, so there is, I want to touch a little bit on the history. As I said, I'm coming from the pulp team, so we'll give some contributions to the team. And then we will have an overview of the microcontroller-based platform. You have seen some early glimpses of that already, hinted by the Quick Logic team, and I will touch on that a little bit more, as well as on the application class-based platform, which I've been mostly involved on a technical level for the past. And then I figured that there was, if there's some time left, that it was always quite a hot topic to ask about how debug actually works with Quive debug. And this is quite a prominent topic and a very important topic, which we are working on in the open group. And last but not least, there is a quick overview on the FPGA platform, and I want to introduce my great team. I put them in the last pages of the slide so that you have the faces, you can remember them, and some pointers where you can contribute if you want to. So as I said, the history of both platforms and the cores so both projects originate from the pulp projects. The Core 5 MCU is derived from a Pulpissimo, which is the second generation single core platforms. We started off with the Pulpino platform, which was a very simplistic but first open source system, which was really widely adopted. And on that success, we were building a second generation enhanced Pulpissimo platform. It is tuned for efficiency, as Davide already mentioned in his talk. This is the primary focus, research focus of our group. And the Core 5 MCU, in contrast to Pulpissimo, has now features the improved verification, improved CV32E40P, as well as a more standardized OBI, Open Bus protocol on the instruction and data interface of that core. We still include the ABB, the Advanced Peripheral Bus System it's an ARM standard for the microDMA subsystem, which ties in a lot of interesting peripherals, which are very interesting for a microcontroller-based platform. On the application class platform, which is derived from Ariane's SoC, and we have renamed and rebranded this as CVA6. This is a Unix-capable system. So the idea was to provide the minimal infrastructure to demonstrate the core and to demonstrate Linux booting of that core, as well as everything is built on AXI infrastructure, which it's quite nice because we can leverage a lot of the existing peripherals which come within the Xilinx platform, which the SoC is built from. So the Core 5 microcontroller platform looks as follows, and if you have seen a first block diagram already, in the middle, the center of the system is the CV32E40P, which is attached to a tightly coupled data memory, and this is a multi-banked memory, and both instruction and data interface are attached to this multi-banked tightly coupled data memory. What this essentially brings you is that you have a unified view, a shared memory architecture for both instruction and data. And through the multi-banking, you can, without conflicts, ideally access instructions and data. On the data memory as well, we have the microDMA engine, which is a smart I/O subsystem, which can copy and interact with a lot of peripherals from different peripherals like UART, SPI, I2C, and so on, without involving the core too much. What's cool with that is that we can really go into a very energy saving mode. We can clock gate the core, and we can let the microDMA handle most of the data movement between peripherals and the multi-bank memory, and only wake up the core or peripherals if we really think that the processing is necessary. Yes, so usually this is quite, because it's a single core system, it's quite a small system, and the idea is that we usually just use it as a controller in a larger system. And for kind of research systems, we do have a compute cluster coupled to this system. And you can, for whatever product or thing where you need a simple but very energy efficient controller, the Pulpissimo platform is the right way to go. I've put a link here. We have forked it into the open hardware group namespace. And as Rick said, the slide's going to be distributed later, so you should have the links. The microDMA, what's really nice is that the DMA is shared amongst the different peripherals, and there's really a large set of peripherals which we can support out of the box. There is a very advanced quad SPI system. There's a camera interface, I2C, I2S, JTAG, GPIOs, interrupt controller, boot ROM, and what is really nice here, custom accelerators. We have here an HWPE, which is it's part of our research, but this case just stands for, any peripheral where you have a control interface and a data interface where you want to process on, and you can really substitute this to whatever peripheral you might want to have. Maybe what I didn't mention so far is we have a special event unit together with standard RISC-V interrupt support, which I will talk about a little bit later, as well as the fast RISC-V interrupt mechanism, which is being standardized. There is an event unit, and this can generate a couple of requests. And what's really interesting is that an event doesn't redirect the control flow and provides a much shorter latency way into signaling the core. So this one is mapped to the APP bus for control interface, has a couple of FIFOs here and there, and is being controlled via a regular load and store, stores. So in principle, any sources can be attached. A couple of sources which are attached in the default platform are timers, GPIOs, and a couple of events from the microDMA. And as I said, if your programming model of the custom accelerator demands an event or an interrupt, you can also attach your custom accelerator. So this one is really an example for a custom accelerator, which is being open source. It focuses very much on artificial intelligence, but any accelerator, being it video decoding or whatever, some crypto accelerators can be, and we have attached actually a lot of them in our research. What's the takeaway point here is that the proposed system, the Core 5 MCU platform, which exists out there, really makes it easy to attach such an accelerator. What you have is you have a variable number of memory ports where you can very efficiently and with high bandwidth can access the shared memory infrastructure, and we provide a small, not so latency sensitive ABB control interface where you can write and read your control and status registers and control the overall operation of the custom accelerator. Now, what this makes really nice is, as we already have touched, that we are going to have an eFPGA embedded in the first ASIC, which is coming out, hopefully, which is planned for beginning of next year. What is really nice is we're going to have two realizations of this microcontroller-based platform. One, we have it on the FPGA. We're going to target the Nexus A7 and the Genesis. So the Nexus you will see in the afternoon, and the Genesis, which is also quite a rich FPGA. We'll have a system for that, and we're going to have an ASIC realization together with the eFPGA of QuickLogic. Now, what that helps you is if you develop a custom accelerator, you can easily prototype that on the FPGA platform. You can harden, you can bake your accelerator in bitstream, but it also allows you to use the very same accelerator description, the high-level description logic, and put that into the eFPGA. And so this dualism is going to be really nice if we're going to target that. And I think this brings me to the end of the microcontroller-based platform. And I'll focus. There is still some software. You will have a hands-on session in the afternoon, and don't miss that, or night here in Europe. So there we will take you through the entire step of building software, running the bitstream on the FPGA. But part of the software is currently still in this PAL platform repository. But eventually, within the effort of the software task group, we want to provide a much more standardized and clean approach of getting software to run on the microcontroller platform. So this brings me to the application class processor platform. And as I said, the idea was to really showcase the core so that it can boot Linux, and we wanted to include a minimum set of peripherals and to make a really stripped down SoC so that one can understand the internals of the system much better without cluttering and making it too complicated. So on the right-hand side, you have the Ariane core with integrated instruction and data caches, and this communicates by a single AXI4 into a kind of a system crossbar. And this system crossbar provides access to the core local interrupt controller and to the platform level interrupt controller. From the platform level interrupt controller, we have external interrupts going into Ariane, and as well as for the core local interrupt controller, we have timer interrupts coming, timer and software interrupts coming from into the Ariane/CVA6, and the timer interrupts are triggered by a real-time clock. What happens if you pull the SoC out of reset? The core is going to start fetching instructions from boot ROM, and in the boot ROM you will have the zero-stage bootloader, which is baked in System Verilog, and which is then essentially going to fetch configure the SPI and copying in data from the card into the main memory, the main DDR memory, which we leverage the existing memory interfaces we can find in modern days FPGAs with hard-baked DDR controllers. And in addition to that, we have a UART, which provides user input. It is like the main UI we have in this SoC. And we figured out that Ethernet is quite interesting to have for network connectivity and remote connection. What's a little bit special over here is that we developed this minimum set of peripherals and minimum SoC to live in the CVA6 core, because it's really like a vehicle to demonstrate the core. But we hope that we eventually can take a unified approach for most, at least this is my hope, for most of the cores within open hardware to really have like a standardized SoC, which is well documented, well verified, and hopefully easy to understand, but still quite versatile. So I figured that would be quite interesting for you folks to understand what is the absolute minimum necessary to actually boot Linux. And so from a hardware perspective, from a core perspective, we either need 64 or 32-bit RISC-V core. We need the atomic extensions, and we need at least three privilege modes, user, supervisor, and machine mode, including a memory management unit. There are, I think, efforts going on to also have a no memory management unit port, but this is really, I mean, Unix needs a memory management unit. There is the need for FND extension, although you can configure them. You can configure the kernel to also go without the FND extension. But what is now more interesting here is what do you really need from an SoC perspective? And the most crucial part, which is always a little bit of a hurdle for us for our research ASICs, is that you need quite a lot of main memory. So 16 megabytes is already pretty much on the short end, and you need a little bit more, usually like 32, 64. And on the FPGA platforms, this is really nice. Because we have the DDR controller, which essentially gives us access to gigabytes of memory. On the interrupt side, we at least need the CLINT, which has the time interrupt, which is needed for the Linux scheduler, and some sort of user I/O, usually a serial console is the UART, as I've told you before. On the software side, we need a zero-stage bootloader, a device tree specification. I will touch on that in a minute. Usually some RAM preparation because the Linux binary, the Linux ELF is assuming some zeroed sections, and the second stage bootloader, as well as the Linux kernel, and a couple of user space applications. On the interrupt side, RISC-V specifies core local interrupt controller, which are like really local to the heart, the hardware thread, which are quite fast to handle. So they have a short latency, but are quite expensive in terms of hardware because they're tied into the core, and there are quite some registers which are associated with that. On the platform level interrupt controller, we really have latency insensitive interrupts, such as the UART and the SD card and that kind of peripherals, where you don't bother too much about the latency. This is going to be part of the Unix platform specification, and we're going to have, and they are a little bit more latency insensitive, and the PLIC provides some more advanced prioritization. And the fast interrupts, this is like the hybrid approach. This is not implemented currently in Ariane /CVA6, but more in CV32. So the device tree is really useful for the sense that how do we detect the capabilities of the platform, so that the core or that the software kind of needs to detect what is available on the platform, what kind of drivers do I need to load. And there's quite a fair specification, the open firmware specification, which specifies the device tree format. And this is usually compiled into a binary blob, which is embedded within the zero-stage bootloader, and then passed on to the next bootloader step in register A0. Usually this is parsed and filtered by each bootloader step. So second stage, third stage, whatever, you can augment or strip down certain things of this device tree to adjust what is visible to the next state of booting. So that alone doesn't really help to boot Linux, because you need a reasonable fast emulation platform. We technically, you could boot Linux in a simulation, an RTL simulation, and we actually did it, but it takes a couple of days to almost a week to boot into almost user space. And what you usually want is to have an FPGA platform. And so we have a default board, which is the Genesis 2. There's quite some widespread adoption of that in academia, mainly because it provides quite a rich set of peripherals on the board, and it is reasonable cheap to obtain for academics. And there is, and please contact Rick or the CMC guys for better. There are discounts through open hardware for this kind of board. The board is not always in super high availability. That is the reason why we have opted for an alternative board, the Nexus A7, which you can see here. It is a little bit cheaper. It has a little bit less loads available, but it has a higher availability, and it also has quite some rich peripherals here, which also makes it interesting to target it as a kind of an emulation platform for the kind of SoCs we are trying to build. And this is really, I think this kind of excites me actually the most, is like that people, so once you see that there is kind of flow in place for those two ports, there are user ports. So people who took the time and effort to try out and to adapt the RTL for their own boards, either because they for their purpose they needed like bigger boards, or that wasn't available for them or too expensive, whatever. And we have actually two user boards supported in the CVA 6 repository. One is the VC707 and the KC705. As well, I think there is some ongoing effort to port the CVA6 SoC also to the larger and unfortunately a little bit more expensive ultra-scale boards. For software, a similar story holds as well as to the MCU platform, is that we provide a very basic SDK. It contains a toolchain, just see that there's a typo. The toolchain which is needed, it's really, as Ariane doesn't really implement specific custom extensions, is really like an upstream GCC extension, sorry, an upstream GCC, as well as build root environment, which helps you build this kind of embedded Linux we are running, as well as the Linux kernel in one repository with a little bit of glue makefile logic that ideally helps you to build those, as well as Linux applications. And we also provide some pre-built images. And I think one of the really important goals here, and Jeremy, I'm pretty sure will touch on that in the afternoon session, is to really build a unified and streamlined approach of obtaining and building those tools. And I really genuinely hope that we can kind of get rid of this proprietary repository at the moment, and eventually embrace a more unified and polished experience. And you really have to see that this has been born out of like an academic necessity, and I hope that we can bring this to an industry standard. And yeah, so there's the point left here on the technical side, is the talk a little bit about the debug. So we have support for the RISC-V debug specification 0.13, which allows you to kind of run, halt, and single step your core. We have the JTAG interface supported, as well as OpenOCD, which is also part of the Ariane SDK you've seen before. What is really nice about that, this is this standard approach, and this allows us to leverage a lot of components, for example, like the Ashling debugger, which I'm pretty sure you're going to be hearing about in the afternoon as well as IDE integration, which is very important to get this to a usable level. So just a very detailed slide. There is the debug is implemented in this execution-based debug approach, in both cores and both SoCs. So you kind of leverage the existing pipeline of the cores to facilitate the debug infrastructure, and you put the core in a dedicated debug mode, which has a little bit of elevated privileges and supports a couple of more instructions. And we also provide a system Verilog reference implementation, which you can find here if you want to engage, and just or just if you just have questions or want to be pointed to more documentation. Yeah, just ask or send me an email. And now, last but not least, I want to really highlight the team. So I have the pleasure of directing two task groups, the hardware and the software task group, which I think really makes a lot of sense because the part of the generated profit of open hardware group is on the boundary between hardware and software. Neither can stand alone. And so on the hardware task group side, we have you who is sharing that, and he will he's also a moderator today, and you will get him to know in the afternoon session on the hands-on. And Tim, who has already spoken, he's the vice chair. He is with QuickLogic, and you is with CMC. And on the software side, we have Jeremy, who is the chair of the task group. He's also the CEO of MBCosm, and Yunhai, who is the vice chair of the software task group, and he's with Alibaba. And I am the director of the both task group, and yeah, my name is Florian. So if that got you excited, please get on board. Development is in the open, so there is no secret repositories or whatsoever going on. This is really everything in the open, and the MCU platform is here, as well as the APU platform, which is, as I said, is directly developed currently in this course repository. And yeah, I think this brings me to the end. Happy to take any questions.
Great, thanks, Florian. Yeah, we had a question pop in asking really around the Core 5 MCU. What would you compare that to in terms of the market MCU? The questioner, the attendee asked, like maybe a Cortex M4 or something. What kind of class of device is the Core 5 MCU?
Yeah, the Core 5 MCU is really like in the range of a Cortex M4. While the APU the APU platform is obviously more like an A6, a lower end application class core.
Thanks, Florian.
Perfect. Thanks.